Welcome back to AlgoJS. Today's question is LeetCode 261 graph valid tree. So we have this graph from nodes 0 to n-1, and we have edges between each node, A and B, and this is an undirected edge. So all we need to do is return true if the edges provided within this tree create a valid tree. Otherwise, we return false. So this is a bog standard graph traversal question, and we are checking for a cycle. So you can see in example 1, we have this tree. It's going to return true because there aren't any cycles. We have this example, example 2, there is a cycle here that we can see, so this is going to return false. So let's work out how we solve this. So with any graph question, we usually have to populate an adjacency list, and this is going to contain the current node and all of the adjacent nodes that it's connected to. So this is going to be 1, 2, 3 for 0. 1 is going to be connected to 0 and 4. Remember, it's undirected, so it goes both ways. 2 is connected to 0. And 3 is also connected to 0. Now we need to check for a cycle within this. So it would make sense to have a visited set to keep track of all the nodes we have visited. And let's run through the traversal, right? So if we start at the root node, okay, we're at 0. This adds 0 into visited. Okay, so we visited it. Now we look at its neighbors. So let's first look at 1. So we recursively call 1. We add 1 into visited. Now we look at the neighbors of 1. We've got 0. So we go back to 0. We check in visited whether there is a 0. 0 is present. We have a problem, right? Because we know that this is a valid tree. However, if we're just checking to see whether the current node that we're on is within visited, this is going to return us the wrong answer. So how do we cover this? How do we stop this from occurring? Well, before we go down to 1, we need to pass something. And what we're going to pass down is the parent, and the parent is going to be equal to 0. So now when we check the neighbors, so if we check 0, if the visited set contains the neighbor that we want to look at, as long as the neighbor is equal to the parent, there is no cycle. So then we look at 4, right? So 1 goes to 4, 1 passes down in the recursive call to 4, the parent, which is going to be 1. At 4, we add 4 into visited. 4, which I forgot to add into the adjacency list, is connected to 1. If 1 is found within the visited set, but the neighbor is equal to the parent, then there isn't a cycle. So if there's not a cycle, we've checked 4, we can pass back up the recursive call, false, right? Because there isn't a cycle. At 1, we've checked all the neighbors, there isn't a cycle, so we pass up false. Then at 0, we can recurse down to 2, passing down the parent of 0. 2 is added to the visited set. We look at 2's neighbors. 0 is within visited, but the neighbor of 0 is equal to the parent, so there is no cycle. So we can return false from this. Then we look at 0's last neighbor. 3, we pass down the parent of 0. So we add 3 into visited. We check 3's neighbors. So 0 is within visited, but the neighbor of 0 is equal to the parent of 0. So just like before, there isn't a cycle here. So we can return up false. So we've checked all the values, and from this, we can return false. And if this returns false, then we know that we have a valid tree. There is just one other check which we haven't taken into account. Say we have this tree, but we also have this as well. So we have a disjointed set, right? There are 2 separate trees. Now, how are we going to check for this? Well, after we've made the check to see whether this is the valid tree, what we need to do is look at the length of the visited set, right? If the length of the visited set is equal to the number of nodes within this tree, then we have a valid tree. If it's not, well then there is a disjointed set, so we return false. So let's discuss the time complexity. For this one, it's going to be O n plus e, where n is the number of nodes that we traverse through within this tree, and e is the number of edges between those nodes. And space is also going to be O n plus e. So let's start this off by creating the adjacency list. When creating the adjacency list, we're going to loop through all the values up to n, and we're going to set adjacency list at I equal to an empty array because we want to include the 0th element in this. Then we can create the connection. So if we loop through A and B of edges, we can set adjacency list at A by pushing in the value of B, and we can do the same for B. So that's the adjacency list created. Now we need to check for a cycle. So if check cycle, so this is going to be the function that we're going to create, passing in the current index, so the current index is always going to start at 0, and the parent, so at 0, the parent is going to be -1. If there is a cycle, we can return false. Right, so let's create this function. So function check cycle. We're going to pass in the current, and we're also going to pass in the parent. We need to create a visited set. So that visited equal new set. Now we can add to the visited set the value of current. Then we can grab the neighbors. So neighbors is going to be the values in the adjacency list at key of current. If there are neighbors, then we're going to loop through those neighbors. We're going to check if visited has a neighbor. So we're going to check for a cycle, but there is that edge case if visited has the neighbor, but the neighbor is equal to the parent, right? So if neighbor doesn't equal parent, right, then there is a cycle. So we return true. Else, if neighbor is found within visited, but the neighbor is equal to the parent, there isn't a cycle. So we just recurse through this. So we check the cycle, pass in neighbor and current as the new parent. If this returns true, then there is a cycle. So we return true from this. Otherwise, if this process completes, we return false. So there is no cycle. Now we need to check if there is a disjointed set, if there are two graphs. And to do that, we loop through from 0 to n. We're going to check if visited has I. So if visited has the index, then we're going to check if visited doesn't have the index. If it doesn't, then we know that there is more than one graph here, so we return false. If that checks out, we can return true because there is a valid graph. Let's give this a run. Submit it. And there you go. Hope you found this useful. Don't forget to like, comment, subscribe, and I'll see you in the next one.